Okay, guys. Hopefully the compound angle formulas made some sense to you while you were doing that. Um, Basically, what I'm going to do right now is use a compound angle formula to show you um, what a double angle formula is and where it comes from. So, pretty much, you don't need to memorize 5 million different things, okay? All that's happening in a double angle formula is that A and B are equal. So in your compound angle formula that we have over here, it's like A plus A instead of A plus B. Okay, so they're just the same. So if I thought about my left side here, so I'm just going to take my left side to do my proof, because remember, we're always going to keep our sides separate. Key for tomorrow when you do trig identities. Let me just thin out my marker there. Okay, so left side equals. So instead of sine 2x, I'm going to write it as the sine of x plus x, and then use the compound angle formula that's kind of upside down on the side there. So it would be sine x cos x plus sine x cos x, which is 2 sine x cos x. So if you're given a double angle, so the sine of 2 times something, you could rewrite it with the 2 out in front, okay? You can show it with a graph if you want. It's just the graph of sine x cos x is not something that you've graphed, but that's another way to do it. But the easiest thing to do is know the compound angle formula, and then you can derive the double angle formulas. And then you don't have to try and remember a million things. And I mean, in our classroom, they're on the wall anyway. But in general, next year, that's probably not going to be the case. So that is sort of what we're doing today. So we're talking about what happens when A equals B. Okay, so your double angle formula for sine is the one that is above, and that's the only one that there is. For cosine, it looks like there are three. Well, there are three different ways to write the same thing, but again, don't try to remember too many things. And then for tan, I wouldn't worry too much about it. I don't know. I just don't use tan ever. If I see it in an identity, I replace it with sine over cos. If I see it in an equation, I replace it with sine over cos. So I don't really use it. If you are going to use it, this is the identity that you're using. And it is a combination of putting sine 2 theta over cos 2 theta. Okay. But we are going to talk about the cosine double angle formulas. Okay, so the first one comes directly from your compound angle formula from yesterday, right? So cos 2 theta, so if I go again left side, equals, and I have cos 2 theta would be the same as cos theta plus theta, right? And then my compound angle formula was cos theta times cos theta, or cos A times cos B, minus sine A sine B, but A and B are equal. So that first one comes just from plugging in to the formula that you saw yesterday on your handout. So that's okay. Left side equals right side. Life is good. The other two just come from using basic trig identities. Okay, so tomorrow is your big trig identity today, but today we're going to remember something we know from last year, which is this concept that sine squared x plus cos squared x equals 1. Okay, so those two other formulas come from rearranging this and plugging it in to this guy. All right, so if you start from here, so cos 2 theta equals cos squared theta minus sine squared theta. If I needed that to be in terms of only cos or only sine, I can isolate what I need to kind of get rid of in this equation here. So I could say, okay, I need something in terms, say I only know the cos of theta. So in terms of cos theta, I can go sine squared theta equals 1 minus cos squared theta. There we go. Okay, and then I can sub that in. So I'll use a little highlighter. So I can take this and replace sine squared with that, right? So then I would have cos 2 theta equals cos squared theta minus 1 minus cos squared theta. And as long as you remember to distribute your negative, that gives you 2 cos squared thetas. Subtract 1. Okay, and that's your other formula. And then you could repeat that by replacing cos squared with 1 minus sine squared theta. And then you would have 1 minus 2 sine squared theta because it would be at the front end of that subtraction in the original formula. Okay, so those are your double angle formulas. Again, I am very unlikely to ask you about tan. If I ever asked it, I would put the formula on the paper. But I wouldn't stress about that. Just make sure you know, like, the pretty much, if you know these, you're good because you can derive the others from that. Okay, so it looks like lots, it's not. Why do we do this? And you're probably wondering that even after yesterday, like why? Why are we doing compound angle formulas? Like what is the purpose? So one is to simplify trig expressions, so to try to write things in a way that looks a little neater. Another spot where they're super useful is to find exact values for trig ratios for angles that aren't special angles. So like pi by 4 is twice pi by 8, so we can use the double angle formula for cosine to find the sine or the cosine of pi by 8. Okay, so there's a lot of kind of uses like that. Not that it's a practical use, but just that it's like a mathematical use. So as you move through university math, you're going to need to be able to do stuff like that. And then the other spot where you use it is just for equivalence, right? So whether that means you're proving a trig identity or you're just rewriting things in a different form. Again, just trying to simplify and neaten things up. Either way, making things that are equivalent, the double angle formulas help us with that. So the first one that's here is here on purpose because for some reason you guys, well, maybe not you guys, but typically students have a really hard time when I just say like rewrite it as a single trig ratio. So what you have to do in that case is look at this and think about like what does it kind of look like, right? So to me, it looks a lot like sine 2x equals 2 sine x cos x. So that's the identity that it kind of resembles in structure. So what I need to do is take what's on this side and write it this way. Okay, so 2 sine 4x cos 4x would be equal to the sine of 2 times 4x. Okay, or the sine of 8x. Okay, so whatever is here is defined as 2x. I know it's weird that it's got x's in both spots, but 8x would be like 2 theta, and then 4x is like theta on its own because you would divide by 2. Okay, so that's all that the question is asking you to do when you see that. And just remember, whatever is here is equivalent to what was here in the original formula. Okay. And then this one is kind of the same idea. Like right now, a lot of you like to just grab a calculator. But if I want an exact value, your calculator is not going to help you a lot when you plug in 3 pi by 8. Okay. So when it says to express it as a single trig ratio and evaluate, that's probably a good idea to actually follow the instructions. So again, I am thinking, hey, that looks a lot like cos 2 theta equals 1 minus sine squared theta, right? And then in this case, theta is equal to 3 pi over 8. So I could rewrite this thing as the cos of 2 times 3 pi over 8. And as long as we multiply our fractions correctly, then I'm going to find out that that's the cos of 3 pi over 4. What I should see always when you guys are working with trig, and remember the exam is going to be me okay? I should always see some kind of a picture. So I know that 3/4 would be over here. So this is like 3 pi by 4. And I know the cast rule. So I know that cos is negative. And I know that my related acute angle is pi by 4. So therefore, the answer to this when I evaluate is going to be negative root 2 over 2, or 1 over root 2, whatever makes you happy. But it's going to be the value of the cos of pi by 4, but negative because it's in quadrant 2. Okay. This is going to be the one time only that I talk about the tan double angle formula, and I'm actually going to have to flip back and forth to actually write it down because that's how much I don't know it. But tan 2 theta equals 2 tan theta over 1 minus tan squared theta. All right. Theta over 1 minus tan squared theta. And in this situation, theta is going to equal 3x because 2 theta was 6x divided by 2. And that's where that came from, okay? So this means then that I would have like tan 6x equals 2 tan 3x over 1 minus tan squared 3x. And then we can't do anything. You can't cancel or anything like that because there's subtraction in the denominator. So that's it. That's all. You've done your work. That's your final answer. Okay. And now our mission is to kind of extend this a little bit. Okay, so we're going to try to figure out the values of sine 2x and cos 2x. And we've been given the idea that cos x is 2/3. Okay, and we are on the interval from 0 to 2 pi. That should be pi. Hold on. Just to make our lives a little bit easier right now so we can have less possible answers. There we go. Okay, so from 0 to pi. Okay, so that means that I know that my angle, if cos is positive, has to be in quadrant 1. Okay, and I know that x is 2 and r is 3. So that was given. If you forget how to figure out sine, you can still find a value for cos 2x here, right? Because we know that cos 2x is equal to 2 cos squared x minus 1. And we know the value of cos x. Okay, so the one that you can find no matter what is this one, because I know that it is 2/3 minus 1. Okay, so cos 2x is going to equal 4/3 minus 1, or 1/3. Okay, and that's true no matter what. So that's your value for cos 2x. It's not the measure of the angle or anything, but it is, I'm trying to make that clearer, I'm making it more of a disaster. 1 over 3, there we go. Okay, so 4/3 minus 1 leaves me with 1/3. You could solve the equation, but that's not really what we're doing right now. You're just trying to find that value of cos 2x. Now, to do sine 2x, we need to know both sine and cosine. Sine x. Ugh. Okay, so we have to know both of those things, and right now we only know cos x, but we can find sine x because remember we can use the Pythagorean theorem, right? Because we're just trying to solve for y. So y squared would be 3 squared minus 2 squared, be 5. So the root of 5. So the sine of x would be root 5 over 3. Okay, and we're going to work with exact values all the time here. And that value is going to be the same always, always, always in quadrant 1 or quadrant 2, right? So sine 2x is going to equal 2 times root 5 over 3 times 2 over 3 Seriously, some of it is bad penmanship, but some of it is just like, I don't know. There we go. Okay. And then you just do the best you can with that. So the sine of 2x is going to be 2 times 2 is 4, root 5, and 3 times 3 is 9. Okay, and that's all it's looking for when it says to determine the values of the ratios. You're not trying to solve for x, you're not trying to find the angles. That's where that interval really, really matters. But right now, we're good. We found our values. Everything is positive because we know where we are in quadrant 1 there. Okay, so that is that. Hopefully that makes sense. Just use the formulas, trust it. Don't freak out because it's trig. Just use the formulas and get used to using them. And then tomorrow when you do trig identities, you'll be able to apply them to hopefully shorten some of the identities that you would have had to take forever to prove last year.